In our last video segment, we brought up something known as the equation of continuity. The equation of continuity says that flow rate is constant. And we can express that mathematically by saying the product of area and velocity at any point remains constant. That would be square meters times meters per second, which would give us cubic meters per second, and that's a pretty good unit of measurement for expressing something like a flow rate. Okay, well, in bringing up this equation of continuity and talking about the rate of flow, we've definitely transitioned from a study of fluid statics, and we've moved on now to fluid dynamics. And one of the key principles of our study of fluid dynamics is expressed in the form of an equation known as Bernoulli's equation. So here's a picture of Daniel Bernoulli, and a situation where you might apply Bernoulli's equation has to do with water flowing through a pipe. But before I even represent this picture down below here as water flowing through a pipe, let's think of it in terms of fluid statics. If I were to ask you, where's the pressure greater, at point 1 or point number 2, you'd probably say point number 1. After all, in our study of fluid statics, we said pressure depends on depth. We said something known as gauge pressure is equal to density of fluid times gravitational field strength times depth. But if water is in motion, then pressure doesn't just vary with depth. It varies with depth and with speed. And we'll come up with an expression by way of Bernoulli's equation that relates pressure differences with not just height, but also with speed. So pressure in fluid statics is a function of depth. So we could either say a function of h, or we can say pressure is a function of vertical position. But when it comes to fluid dynamics, we have to say that pressure is a function of both vertical position and velocity. Okay, so let's think about this. Instead of picturing this as a bunch of static water in a contained pipe, let's picture it as water in motion. So the fluid is flowing to the right, and let's pick just a portion of this fluid. So let's say we've got a segment of, and our fluid in this case might as well be water. So let's say we have a segment of water that takes up that much volume. We'll call that much volume dV, and that amount of water has a mass we'll call dm. Now, as it exits this shaded region and moves on to the right, then at some point it's going to occupy this space, and in doing so, then it's traveled a displacement. The water has left here and traveled a distance, we'll just call it x number 1, and then it continues to move and get up into the higher elevated part of the pipe. Because the pipe's constricted, to represent that same volume, you would have to take up a greater length. So maybe that much shaded area represents the same amount of volume dV with the same amount of mass dm. So the only reason this water would be flowing to the right is if there's pressure that pushes to the right at point 1, and there's some pressure that creates a force that pushes back to the left at point 2. So the water's flowing with some velocity, v number 1 at position 1, and then the water flows with perhaps a different velocity, v number 2, when it reaches this greater height. So we've got a few variables that are all interconnected. We've got position number 1, vertical position number 2. We've got a velocity number 1 and a velocity number 2, and a pressure number 1 and a pressure number 2. We can express how all these quantities are interrelated by applying the Work-Kinetic Energy Theorem. So hopefully you recall the Work-Kinetic Energy Theorem says the sum of all work done on an object is equal to that object's change in kinetic energy. So here again we've got our volume dV. So think of this as the exact same body of water at a later point in time at the elevated segment of the pipe. As the water moves from point 1 to point number 2, there are 3 forces working on it. There's force number 1. Oh, and by the way, if pressure is force divided by area, then force is pressure times area. So if there's a certain pressure at point 1, that creates a force number 1 that can be found by multiplying pressure 1 times area 1. And likewise, force number 2 is pressure 2 times area 2. Okay, so right, there are 3 forces. There's F1, F2, and then of course there's force of gravity pushing downward. So the net amount of work is the work done by gravity plus the work done by F1 plus the work done by F2, and all of that work summed up has to equal change in kinetic energy. Okay, work done by gravity. Let's see. The force of gravity points down, but the water's displacing upward, going from a height of y1 to y2. So work done by gravity, because the force and displacement are in opposite directions, should be negative mg times delta y. The work done by force number 1, well, force number 1 points in the same direction as the displacement. So work done by force number 1 is F1 x1. Work done by force number 2 should be negative. Force 2 points to the left, but the water travels to the right, a displacement of x2. So this, it will say minus F2 x2. Change in kinetic energy is 1/2 mv squared. Oh, I suppose what I mean here is dm. We're just imagining that this is a small fractional amount of mass moving through the pipe. So this is 1/2 dm velocity 2 squared minus 1/2 dm velocity 1 squared. Okay, let's see. This is negative dm g y2 minus negative dmg y1. So we can get rid of delta y by saying it's the same thing as y2 minus y1. Plus, let's see, force number 1 is pressure 1 times area 1. And we still have to consider x1 minus pressure 2, area 2, x2 equals 1/2 dm v2 squared minus 1/2 dm v1 squared. Now, look at this. What is area 1 times x1? If I multiply this cross-sectional area times this amount of distance, then that just calculates that volume occupied. So this is dV. In the same way, area 2 times x2 represents the same amount of volume, dV. So I'm actually going to divide both sides of the equation by dV to cancel that out. And what does that get us? This gets us negative dm over dV times g times y2. Let's see, negative creates positive, so positive dm over dV g y1 plus p1 minus p2 equals 1/2 dm over dV velocity number 2 squared minus 1/2 dm over dV velocity number 1 squared. Okay, let's see. I guess we can get everything with a subscript 1 on one side of the equation and everything with a subscript 2 to the other side of the equation. This would give us dm dv gy1 plus, let's take this negative term on the right side of the equation and bring it over to the left side of the equation. So plus 1/2 dm dv velocity number 1 squared plus p1 equals, then I can take this negative term and this negative term and bring them both to the other side of the equation. So we get dm dv gy2 plus, we already have this expression on the right side of the equation, so plus 1/2 dm dv v2 squared, and then plus p2. But of course, what is dm dv? What units do we have when we express kilograms per cubic meter? Well, that's just density. And density is the symbol rho. So we could say that this expression is P1 plus rho g y1 plus 1/2 rho v1 squared equals P2 plus rho g y2 plus 1/2 rho v2 squared. And that is Bernoulli's equation. And notice it gives us just what we expected, that pressure, or changes in pressure, is a function not just of height, but also of speed. So pressure doesn't just vary with depth. Pressure varies with depth and velocity for fluids in motion, or what we call a study of fluid dynamics. So in our next video lesson, we'll come up with some examples of how we can apply Bernoulli's equation.